All right, Maya, let's dive right in. We're looking at a paper from a team at the University of Oxford and others titled Ad-Hoc Human-AI Coordination Challenge.
The abstract gets straight to it. Seamless coordination between AI agents and humans is a massive open challenge. They propose using the cooperative card game Hanabi as a testbed because it's full of imperfect information and requires coordinated action.
And they're open sourcing a small data set to encourage researchers to build data-efficient methods. I like that. They're not just solving a problem, they're building a whole community challenge around it.
Moving to the bottom half of page 1, we get into the introduction. They really set the stage for why this work is so important.
They do. They mention that as AI gets more integrated into our daily lives, from healthcare to autonomous vehicles, this kind of effective coordination becomes critical. The goal isn't just an AI that can solve a problem, but one that can work with a human in a human-compatible way. And they touch on a classic AI training method, self-play, where AI is trained by playing against copies of themselves. That sounds good in theory, but what's the problem?
The problem, which they lay out clearly, is that in cooperative games, self-play agents can overfit and create rigid conventions or specialized strategies. Think of it like developing a secret code. It works perfectly with your twin, but a total stranger or a human would be completely lost. This can even be a safety risk.
Okay, that brings us to the top of page 2. They continue the introduction by highlighting the lack of standardized benchmarks in this field.
Right. They state that without open and robust benchmarks, it's hard to measure progress consistently. Many existing methods use closed datasets or proprietary agents, which hurts reproducibility. To fix this, they introduce AH2AC2 as a standardized way to evaluate human-AI coordination in Hanabi.
And they give us a peek under the hood of their human proxy agents. How are these built?
It's a two-step process detailed here. First, they use behavioral cloning, or BC, which is essentially training an AI to imitate human actions from a huge dataset of over 100,000 human games. Then, they refine that policy using reinforcement learning, specifically IPO, with a regularization term that encourages the agent to stick to human-like behavior.
So, imitation first, then refinement. And to keep the challenge fair, they are not releasing the proxy agents themselves, just a smaller dataset for training. They also provide a whole suite of baseline agents to compete against.
Yes, and it's a great list of baselines. They have methods that use no human data, like off-belief learning, data-dependent ones like best response to behavioral cloning, a population-based method called fictitious co-play, and even an agent built on the large language model DeepSeek R1.
Now, the bottom half of page 2 gets a bit more technical with the background section. Maya, can you decode the DEC poem DP for us?
So it's the formal way of saying, you're on a team, you can't see everything, and you have to work together.
And they briefly describe Hanabi. Players can't see their own cards and rely on hints from teammates to play cards in sequence to get a max score of 25.
Page 3 is dominated by Figure 1, which is a fantastic flowchart of the entire challenge. This really helps visualize the process.
It does. On the left, you have what's provided to participants. This includes a subset of the human play data and the code for baseline agents. Participants use this to develop their own human-compatible agents. And then the evaluation loop on the right is where the magic happens. The community-developed agents are sent to an evaluation API.
Exactly. That API gives them limited access to the human proxy agents, which are in the closed source box at the top. These proxies were trained on the massive, private human dataset. The agents play together in an ad hoc team play scenario, and the results go on to a public leaderboard. It's a really well-designed system for fair and reproducible evaluation.
Okay, on to the top of page 4, which starts with related work. They position their work against what's already been done in the Hanabi world.
They note that most of the progress in Hanabi has been in self-play, where agents achieve near-perfect scores but can't generalize to new partners. The real challenge is ad hoc team play, especially with humans.
So how have others tried to solve this ad hoc problem?
Some approaches focus on creating a diverse set of AI partners for testing, but this paper argues that the most natural and valuable partners to test against are human policies. They also mention that while previous works have explored this, there hasn't been a standard evaluation approach, which is the gap AH2AC2 aims to fill.
The bottom half of page 4 is where we get the nitty-gritty of the challenge methodology. They start by describing the dataset.
Yes, Section 4.1. They collected a huge dataset from Hanabi.live with over 100,000 two-player games and 46,000 three-player games. Importantly, these games all follow what are called H-group conventions, which are a set of handcrafted strategies used by the human players on that platform.
Is that a problem? Does it mean the agents are only learning one rigid strategy?
They argue it doesn't, because H-group conventions are more like a collection of strategies that players mix and adapt. So, the dataset naturally contains a variety of playstyles. Out of this massive dataset, they open source a much smaller slice, 1,858 two-player and 1,291 three-player games for participants to use.
And the challenge itself has two parts.
Correct, as outlined in Section 4.2. Part 1 is the main event, coordinating with the human proxies, where performance is measured by the game score. Part 2 is an optional action prediction task, where the agent has to predict what a human would do in a given situation, measured by cross-entropy loss.
The top of page 5 continues the deep dive into their methodology, specifically how they built the human proxy agents.
This is the core of their Human Data Regularized IPPO, HDR-IPPO method. As we mentioned, they first train a behavioral cloning, BC policy, on the large human dataset. They model this policy using an LSTM-based architecture, which is good at handling sequential data like a game history.
And a key point they make is that even though the AI's neural network parameters are fixed, its behavior isn't static. It can adapt based on the game history, including a partner's unexpected moves. So it's a balancing act. Get better at the game through RL, but stay anchored to human-like play. And they lay out 3 ways they're going to validate that these proxies are actually human-like.
On the bottom of page 5, they finish explaining the validation and move on to the evaluation details. Let's start with Table 1.
Table 1 gives us statistics for the small, open-sourced dataset. We can see that the human players in this dataset are very good. For both 2-player and 3-player games, the average scores are high, 23.37 and 23.25 out of 25 respectively, and the median score is 24. This tells participants that they're training on data from expert human players. And they recap part 2 of the challenge, action prediction, where the goal is to have a low cross-entropy loss, indicating your AI thinks like a human. Then, in section 4.3, they talk about the API and leaderboard.
This part is all about ensuring fair and rigorous science. To participate, you register on their website, ah2ac2.com, and get a private key. This key allows a one-time evaluation run of 1,000 games against the proxies to prevent people from just overfitting their agents to the proxies through repeated testing. It's a great example of putting best practices for empirical research into action.
Page 6 is all visuals. We have Figure 2, which shows the crossplay performance for both the 2-player and 3-player settings. Maya, what are these heat maps telling us?
These heat maps are really interesting. They show the average scores when different agents are paired together. The agents are the human proxies, HP1, HP2, etc., and the basic behavioral cloning agents, BC1, BC2, etc. The color scale goes from red for low scores to green for high scores.
In Figure 2A, for the 2-player setting, it's a sea of green.
It is. The HP agents play very well with each other, scoring around 22-23 points. Crucially, they also play very well when paired with the BC agents, which are the pure human imitators. This is strong evidence that the HDR-IPPO refinement didn't make them lose their human-compatible conventions.
But Figure 2B, the 3-player setting, is a different story. There are some angry red and yellow squares there.
Very different. When the BC agents, BC3, BC4, have to play with each other, their performance is terrible. Mean scores of 4.87 to 7.28. This shows how brittle pure imitation learning can be. But look what happens when you team them up with a stronger HP agent. The scores jump dramatically. This suggests the HP agents can carry the team, retaining enough human strategy to coordinate even with these weaker partners.
Let's move to the top of page 7, section 5, analyzing and validating the human proxies. They start by looking at the self-play scores in Table 2.
Table 2 is very clear. It compares the final human proxy, HP agents, against their initial behavioral cloning, BC versions. In every case, the HP agents refined with regularized RL, show a significant improvement in their mean self-play score.
The improvement is especially massive in the three-player setting.
Absolutely. The scores for the three-player HP agents are 20.88 and 21.21, which are huge improvements of 15.7 and 13.9 points over their BC counterparts. They explain that the original BC agents were so brittle they would score 0 in over 70% of games, whereas the refined HP agents only score 0 in less than 0.4% of games. This really highlights the robustness gained from the RL refinement.
The bottom half of page 7 is where they really hammer home the human likeness of their proxies. They start with action prediction in Table 3.
Right, so Table 3 looks at how well the HP agents can predict human actions on a hidden test set. The key takeaway is that even after all that RL training to make them stronger players, their accuracy and loss metrics are very similar to the pure BC policies. The loss difference to BC is tiny, just 0.05 to 0.08.
And they report top 10% accuracy, which is quite high, around 82% for two-player and 73% for three-player. What does that mean?
It means that the true human action was in the top 10% of the actions the proxy thought were most likely. Since there are many valid moves in Hanabi, this is a better metric than just top 1 accuracy. It shows the agents have a very human-like sense of what good moves are.
Then they seal the deal with Table 4, looking at behavioral metrics.
Yes, they use 2 metrics: IPP, information per played card, and communicativeness. IPP measures how much an agent knows about a card it plays, and communicativeness measures how often it gives hints. As you can see in Table 4, the values for the human proxies are nearly identical to the values from the actual human dataset for both 2-player and 3-player games. It's very strong evidence that these proxies don't just play well, they play like humans.
Page 8 brings us to the main event. Section 6, Results of Baseline Methods on AH2AC2. This is where they put their new challenge to the test with a variety of existing AI methods.
They line up a comprehensive set of baselines. We have IPO, a standard reinforcement learning agent trained in self-play with no human data.
BC, the basic behavioral cloning agent, trained only on the limited open-source human data.
HDR-IPO, their proposed method, which builds on BC with regularized RL.
BRBC, an agent trained as a best response to a fixed BC policy.
OBL, off-belief learning, a strong method for zero-shot coordination that uses no human data.
OP and FCP, 2 other coordination methods.
DeepSeek R1, a powerful large language model, prompted to play the game without any specific fine-tuning. So they're testing everything from pure self-play to pure imitation to these more advanced hybrid and zero-shot methods. And they even bring in a big gun, an LLM, to see how it fares.
Correct. And they are very careful with the setup. For the methods that use the human data, BC, BRBC, HDR, IPO, they train them only on the small public dataset to simulate the real challenge conditions. They also use different random seeds than the ones used for the human proxies to ensure fairness. And page 9 delivers the results in Table 5, the official AH2AC2 leaderboard. Maya, break it down for us. Who's on top?
The results are fascinating and highlight the difficulty of this problem. In the 2-player setting, the surprising winner among the baselines is OBL, L4, with a mean score of 21.04. This is a zero-shot coordination method that used no human data at all. It outperforms all the methods that were trained on the small human dataset.
Wow. So the agent that never saw a human play beat the agents designed to imitate humans. What does that tell us?
It reveals a significant research gap. It shows that current methods are not able to effectively use small amounts of human data to improve coordination. The best data-driven method was BRBC, but it still fell short of OBL.
What about the 3-player setting?
OBL wasn't evaluated there due to a lack of pre-trained weights. Here, the top performer is actually DeepSeek R1H Group, the large language model that was given the H group conventions in its prompt, scoring 14.62. It outperforms HDR IPO and BRBC.
So the LLM shows some promise, especially when given the rules of engagement. But the overall scores are much lower than the human proxy's own scores, which are listed at the bottom of each section for reference.
Exactly. The human proxies trained on the massive dataset score 22.76 and 20.86, respectively, setting a very high, golden standard. The leaderboard shows that all current methods have a long way to go to reach that level of human-compatible performance, which is exactly what a good benchmark should do. Highlight the challenge that remains.
We're on the home stretch of the main paper now. The top of page 10 is section 7, the conclusion.
They wrap it up nicely. They state that they've introduced AH2AC2, a new evaluation framework for human-AI ad hoc team play in Hanabi. The key innovation is the use of human-like proxy agents, which were generated from a large-scale human dataset to provide a meaningful and scalable evaluation.
They also emphasize that their baseline results highlight how challenging this problem really is, and they invite the research community to participate to push the boundaries of human-AI collaboration.
They then list several promising directions for future work. They suggest a deeper theoretical analysis of their HDR-IPO method, extending the benchmark to cover variations of Hanabi, and conducting experiments with actual humans playing against their proxy agents to validate them further.
And they specifically call out the need for a more comprehensive evaluation of agentic LLMs, noting that Hanabi is an excellent benchmark for testing an LLM's theory of mind.
Maya, that concludes the main body of the paper, but there is a massive 25-page appendix here. We're not going to go line by line, but there are some real gems in here. Let's start with page 13. Appendix A1 and A2 on page 13 give more background on the rules of Hanabi and the technical details of PPO and OBL. It's a good resource for anyone unfamiliar with the game or the algorithms. Page 14 gives us more training details and additional results. What do tables 6 and 7 show? Tables 6 and 7 show the cross-entropy loss on the test set for the various agents. They confirm what we saw in the main paper. The agents trained on the entire dataset, like the human proxy, are much better at predicting human moves, lower loss, than the agents trained on just the small open-source dataset.
Now let's jump to the really interesting part about the human proxies. Page 15 starts Appendix A5.
Yes, Table 8 on page 15 gives the stats for the full massive dataset used to train the proxies. It's huge, over 100,000 two-player games. And page 16 gets into the nitty-gritty of the proxy architecture in Table 9 and the hyperparameter search in Table 10. But the most crucial part starts at the bottom of page 16, role of regularization.
They want to prove that the KL regularization term, the thing that keeps the agent tethered to human behavior, is actually necessary. What did they do?
They ran an experiment where they trained new agents using the exact same procedure, but they set the regularization weight, lambda, to 0. And the results, shown in the heat maps on page 17, figure 3, and page 18, figure 4, are striking.
These look like the evil twins of the heat maps from page 6. Lots of red. Let's skip ahead to the behavioral analysis on page 19. They analyze a single game, turn by turn.
This is my favorite part of the appendix. They go through a 65-turn game played by their human proxies and evaluate whether each move followed the H-group conventions. The final tally at the end, on page 21, is amazing. The agent successfully followed the conventions on 88% of its moves, and even the mistakes it made were described as very human-like, like confusing one convention for another.
It's incredible validation. They're not just showing us statistics, they're showing us the agent thinking through a game. Now, what about the full ablation study starting on page 22?
Appendix A8 is a deep, systematic study of that regularization weight. They train a whole family of agents, varying lambda from 0 all the way to 0 to 70. The cross-play matrix on page 24, figure 5, tells the whole story.
Finally, let's wrap up with the LLM prompts. Starting on page 30, Appendix A10 gives the exact prompts they used for DeepSeek R1. This is fascinating.
It's a masterclass in prompt engineering. They have 3 parts. First, the Hanabi rules prompt, which is a multi-page, detailed explanation of the game. Second, and this is the key, the H-group conventions prompt on page 32, which explicitly teaches the LLM the special coordination rules that the human players use.
Things like the chop card, play clues, and save clues. They're literally teaching it the team's playbook.
Exactly. And the final part of the prompt, on page 36, is the Hanabi state prompt. It dynamically feeds the LLM the current state of the game in natural language and asks for its best action and rationale in a structured JSON format. This is why the LLM performed so well in the 3-player challenge. It was given a massive head start with these detailed instructions.
Wow, what a paper. They didn't just propose a solution, they built an entire ecosystem to test it, validated it from every conceivable angle, and then left the door open for the entire research community to come and play.
It's a fantastic piece of work. The creation of the human proxy agents is a huge step forward, and the challenge itself provides a much-needed standardized benchmark. The results show that we still have a long way to go to create truly collaborative AI, but this paper gives us a clear roadmap and the tools to get there.
And if you enjoy these deep dives into machine learning, please take a moment to like this episode and subscribe to Deep Learning Education so you don't miss our future work.
That's all the time we have for this episode of Paper Cuts. A huge thanks to the authors for this incredible work. Join us next time as we slice into another exciting paper.